Module 3 Homework Video Solution Manual. Number 1. What is the total number of gender sequences when a couple plans to have 8 children, 5 children, and 10 children? We're starting with the MN rule here. And as you recall, we always have to designate the number of positions and the number of choices for each position. So for the first one, how many gender sequences are possible when a couple plans to have 8 children? We're going to have 8 positions. So 1, 2, 3, 4, 5, 6, 7, 8. And so 8 children. And each one, we have assumed for the sake of simplicity, we have 2 genders. So each position has 2 genders. So there are 8 of them. So this is the first position, this is the second position, this is the third position, this is the fourth position, and so on. Fifth, sixth, seventh position, and eighth position. So these are the positions, always, and these are the number of choices for each position. And the MN rule says, basically multiply them together, which is basically 2 to the power of 8. So this becomes, if I erase this, basically the first one becomes 2 to the power of 8, which is 256. So there are 256 different gender sequences. And same procedure applies to parts B and C. Part B has 5 children, so I have 5 positions, 1, 2, 3, 4, 5, and each child could have 2 different genders. So basically this one is just 2 to the power of 5 if I use the MN rule and multiply them all together. So this one becomes 2 to the power of 5, which is 32. So there are 32 gender sequences. Again, same as 10 children. Here you have 10 positions. And 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And each one has 2 choices. So this one becomes 2 to the power of 10. Which is 1024. And you notice from what's happening here is that at least you could look at it as a sort of a formula as to what can I do to get the answer faster instead of drawing like 10 positions every time and all that. Well, if you recognize that this type of problems, whether it's the gender sequencing or coin tossing, if I ask you what's the total number of coin tosses when a coin is tossed, I don't know, 3 to 8 times, 5 times, or 10 times, it would have been the same because gender and coin and a whole bunch of other experiments all have 2 choices, 2 possible outcomes. So therefore, we could come up with some kind of a fictitious formula of some sort, if you call it that, and you could just call it 2 to the n, and for such exercises from now on, you could always use this 2 to the n thing to figure out the total number of gender sequences. So if it's like 15 children, it'll just be 2 to the 15th. 9 children will be 2 to the 9. 12 coin tosses will be 2 to the power of 12. So it's always 2 to the power of the number of coin tosses or number of gender sequences that they're asking you. That's a quicker way to do it. It's still the MN rule, but it's just a sort of a shortcut, back alley way to look at it. Excellent. So let's move on to the next one. How many ways can 8 children be arranged in a queue? So you have 8 positions. So you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 positions. How many ways can 8 children be arranged in a queue? Well, the first position, any 8 of them could stand on this position. This is the first position, second, and so on. 4th, 5th, 6th, 7th, and 8th positions. So in the first position, any of these 8 children could be standing, so it gets 8 choices. But once one of them stands there, then there's 7 left to stand on a second position. And then there's 6 of them left to stand on the third position, and so on. And here, again, you just multiply them all together. Right? And you get 4,320 if you do that. And I'm just going to write the answer here, 40,320. So there are 40,000 different ways, 40,320 different ways 8 children could be arranged in a queue. That's crazy, counterintuitive, but it's true. Same as the other one. 5 children has to be arranged. There's 5 positions. 1, 2, 3, 4, 5. Any 5 of them could be in the first position, but once one of them is stood up there, then there's 4 of them left to be in the second position, and so on. So again, this is a product of 5, 4, 3, 2, 1, which is 120. And then 10 children will be 10 positions. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. And then any one of them could take the first position in line, and then 9 of them left to take the second position, and so on. And if you multiply all that out, you get a large number. You get 3628800. So basically 3.6 million combinations, or different sequences. Now, here there's also a back alley, just like this one, that you could do. See, we did this with the MN rule, and we said, well, there's a formula that could replace the lengthy process of drawing positions and filling out the choice, so you could just use the 2 to the n formula. And same here, when you notice, if the MN rule goes all the way down to 1, which basically means if the number of positions is equal to the number of choices, then if you notice here, and if you remember that special mathematical function, the MN rule here behaves like a factorial rule. So again, we do that so the process of multiplying all these numbers together becomes easier. It takes a long time for you to sit there, whether you use Excel or a handheld calculator, to sit there and say 10 times 9 times 8 times 7 times 6 times this. Takes a long time. It's much faster to do it with that back alleyway, meaning that you recognize that the MN rule goes all the way down to 1, and if the MN rule always goes all the way down to 1 in terms of product, which means the number of choices is equal to the number of positions, then the MN rule behaves like a factorial rule. And therefore, we could very simply, instead of all this work here, we could just erase this and say, okay, well, if that's the case, then if somebody tells me how many ways can you arrange 8 children, that'll be just 8 factorial. How many ways can you arrange 5 children in a cube? 5 factorial. How many ways can you arrange 10 children in a cube? Be 10 factorial. And it's just a faster way of getting to the answer using a mathematical function, which is the factorial. Now, by definition, n factorial means n times n minus 1 times n minus 2, and so on. Basically means like 4 factorial means 4 times 3 times 2 times 1. Now, of course, there's a command for that. There's a factorial button on the calculator, but since we don't use calculators and use spreadsheets, the factorial command for spreadsheets is simply equals fact, parentheses, whatever factorial you're trying to find. So if you type fact of 8, you get 40,320. If you type fact of 5, you get 120. If you type fact of 10, you get 3.6 million. So that's that. So the shortcut here is 2 to the n. The shortcut here is n factorial. And that's a second type of MN rule. And then the third one is another one, which is the combination, and that's all we're going to do. We're going to do the MN, the pure, I call it the pure MN. And then this one is the MN that behaves like a factorial. And then these ones that are being, and the keyword here is groups. So basically it's asking you how many different groups of size 3 can you create from 8, and if that's the question, then we call that the combination rule. And these are the 3 rules you have to be comfortable with. And you've seen the formula for the combination rule is just a combination of 8 choose 3. For the second one, with combination of 5 choose 3. And for the last one will be combination of 10 choose 3. That means combination of 10 people being put in groups of size 3. And for that one, there's a formula, of course, and I'm going to write the formula here. No, I'm not answering this question, just the extension of this. I'll erase it. So combination of n choose k, there's a formula, and you've seen it in the lecture notes. It's just k factorial over n minus k factorial. So there is an algebraic process to do it. But that's for an algebra class, and this is not an algebra class, so we're just going to use a spreadsheet command to find our combinations, and the combination command in Excel is equal to combin, parentheses, the top number, comma, the bottom number. So the combin of 8, choose 3. So that's what you type here to get the answer for combin 8, choose 3, which is 56. You could try that yourself. And then I'll do the combination of 5, choose 3, that'll be 10. And combination of 10, choose 3, which is 120. So you guys could verify these results. And the shortcut formula here is combination of n choose k. So these 3 red circles represent the 3 back alley ways of actually finding the answers easier than looking at it from an MN point of view. Moving on, let's look at number 4. It says, how many different 3-letter passwords could be formed from the letters of the word universal? Now, the word universal has 9 letters. So I'm just going to write that. These are the total number of choices. Because you have to use letters to create this password, so the letters become the choices. So you have a choice of which letter to use for which character of the password. Now, we have how many? 3 different letter passwords, so obviously there are 3 positions here. And it says order matters, so you can't just use the same letter twice, use it once each. So basically they cannot be repeated is what that means. Now, how many choices do you have for the first position, second position of your password character, and the third character? Now, you could choose any of these 9 letters for the first one, but since it can repeat, you only end up with 8 choices for the second character, for the second position of your password, or second character of your password, and then you end up with 7 choices for the last character. It's pretty straightforward, and basically it's the MN rule. So again, these are the number of positions, and these are the number of choices. So the answer is 9 times 8 times 7, which is 504. And that's the final answer. Next, let's move on. How many different 3-letter passwords? Again, here we have 3-letter password. Same problem, can be formed from the word universal. Again, same group of choices I have, but this time it says order does not matter. So you could use any order you like, so they could repeat, right? And it says use the combination rule. If it did, we would have used the MN rule, which is the previous one right here. It didn't. I used the MN rule. If the order doesn't matter, then this becomes a combination issue. So you're basically trying to figure out how many 3-letter group of words can you create from 9 letters. So it'll be a combination of 9 choose 3. And if you type equals combination of 9 choose 3, 9 comma 3 on Excel, you get an answer that's 84 different ways. Okay, and one more way of looking at it, how many different 3-letter passwords can be created from the word universal? This one says with repetition, so this is the MN rule. And this one allows repetition. That means any of these 9 letters could take the first position, but since you could repeat the letter, then you also have 9 choices for the second position and 9 choices for the third position. So this is that version of this. See, I've given you like 3 different versions of the same problem, so you could see how it could come at you on the exam. All right, and the last one is just 9 times 9 times 9, which is 729. And that's how many ways there are. Okay, moving on. Again, we're all just practicing this MN rule, counting techniques. How many ways can 5 pencils and 4 books be organized in a drawer? So again, we start to do this problem. Our thought process is, again, first and foremost, how many positions do I have? Well, it looks like you have 2 positions. You have the pencils and you have the books. So these are the positions. And now let's look at the choices I have for pencils. I have 5 choices for the pencils, and I have 4 choices for the books. And the total number of combinations, basically the product of the 2. And these are the number of choices. So the answer is 20. Moving on, how many ways can 6 senators be arranged around the table? Well, you can look at it from the MN point of view. You have 6 positions, right? And then 6, 5, 4, 3, 2, 1. But since we talked about this backdoor way of doing it, then here I recognize that I have 6 positions and 6 choices. The number of positions is equal to the number of choices here. Therefore, I could use the factorial rule as a back alleyway to get into the code, sorta. So that'll just become 6 factorial, and that's 720. Now, of course, if you didn't see that, you could have put 6 positions, 1, 2, 3, 4, 5, and 6, and say you have 6 choices, 5 choices, 4, 3, 2, 1, or to behave like a factorial anyways. So either way, you'd have gotten 720. But it's easier to use the shortcut way. All right, how many groups of size 4 could be created from 6 senators? So the moment you see the group, it reminds you that it's a combination problem. So this becomes combination of 6, choose 4, which is 15. Excellent. Moving on. Again, just practicing the same thing. How many 3-digit pins can be created from these 6 characters? So my position is 3, so I have 3 positions. Here it says the digits can repeat. So I have 6 choices for the first position, but since they can repeat, I get 6 choices for the second and 6 choices for the third position. Again, this is the first position, this is the second position, a third position, and these are the choices. And 6 times 6 times 6 is 216. The other one says they cannot be repeated, so the positions don't change. You still have 3 positions, but now they cannot repeat. So if you have 6 choices for the first position, you only get to have 5 choices for the second and 4 choices for the third. And this is pure MN rule. And that's just 120. And that's the answer for that. Moving on, and same talking, have 15-digit password. Now the first one says digits can repeat. So you have 15 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you have 15 positions. Your choices are digits, and so you know there are how many digits in this world? 10 digits in this world. In our world, 0 to 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, basically your dial pad on your cell phones. So you have 10 digits possible in this universe for our species on planet Earth to use. Now, if the digits could repeat, that means you could use any of those 10 digits for the first character, any of them for the second one, any of them for the third one, so this becomes a product of 15 tens. Big number. So this is just an MN rule. All of these 10s are going to get multiplied by each other, so it's basically 10 to the power of 15. 10 multiplied 15 times by itself, and that's 1 with 15 zeros. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That would be a nice checking account balance to have. But anyways, that's the total number of ways. I mean, there's like infinitely many passwords you can create for 15 digits if the digits could repeat. Now the second one says they cannot repeat. Now I'm going to use the same picture because I don't want to draw all this stuff again. So I'm just going to use the same picture for that concept. Remember, we already have the answer for part A. So part A, that's the answer. Now I'm going to do part B. It says this time the digits cannot repeat. See, there's a problem. If the digits cannot repeat and you have 15 positions and you only have 10 digits, you say, okay, the first one get 10 digits, and then the second, so they cannot repeat, so therefore you can't use the same digit twice, so the second one you get 9 choices, 8 choices, 7, 6, 5, 4, 3, 2, 1 choice, and then how about the rest of these? So basically the question is, how do you create a 15-digit password if you only have 10 digits and they can't repeat? So it's kind of obvious. So therefore the answer for this one is impossible. Great. So let's move on to some more of these questions just so we can get used to it. Professor Badalian has 8 test problems on data analysis and 5 questions on probability. How many ways can he select one of each? So again, this is a straightforward 2 positions. Data analysis is the first position. Probability is the second position. You have 8 test problems for data analysis. You have 8 choices of questions for that. And you have 5 choices of questions for probability. And that's basically 8 times 5, which is 40. Yeah, I know, you can't believe it's that simple. Enjoy it. So a test has 5 true-false questions. How many different ways can the answers be given in these 5 questions? So part A, 5 questions. So 1, 2, 3, 4, 5 positions. They could be true, false. That means each one has 2 different possibilities. So that will just be 2 to the power of 5, which is 32. And then the other one says, what is the probability of getting the correct answer? Well, the probability I know is a fraction of part divided by the total. The total I figured out is 32. That always goes to the denominator. And the probability of getting, you getting the correct answer is just only one way you can get the correct answers, is a 1 out of 32. And since we have to leave the final answers in module 3 as 3-digit decimal values, it'll just be 0.031, basically 3%. Just for you to get a feel for what it is. Fantastic. Okay, let's move on, guys. Here you have a certain car is available in red, black, silver, white, and blue. Could be purchased in 2 or 4 doors, leather and cloth, sunroof, no sunroof, and manual and automatic. So these are all number of choices. So all you have to do to figure out the total number of possibilities is just multiply these choices together. So first, I get how many choices? 1, 2, actually let me use my lighter. I get 1, 2, 3, 4, and 5. So you have 5 choices for the first one. Then you get 1 and 2 choices for the second one, 1 and 2 choices for the third position, 1 and 2 choices for the fourth position, and 1 and 2 choices for the fifth position. So this basically becomes 5 times 2 times 2 times 2 times 2. And that is equal to 80 different possibilities. Excellent. So let's look at how many ways can a traveling salesman travel to 50 states. Again, you have 50 positions, and then the first you get 50 ways you can go, then 49 ways, then 48 ways. So basically, again, you could use the backdoor thing for this. And recognize that this is basically 50 factorial. And if you do that on Excel and type fact of 50, you're going to get a huge answer. And the answer is going to look like 3.04. Actually, on Excel, it will look like E plus 64. That's what you'll see. And this is known as scientific notation. If you haven't seen this before, this basically means 3.04 times 10 to the power of 64. That's what it means. And that's just a large number, and scientific notation was discovered to write very, very, very tediously long, huge numbers in a very compact form. Because if somebody wanted to write this out, you'd have to basically write 304 and then count 64 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You have to go all the way to 64. So it's a huge number, right? And that's why they write it like that, because, you know, writing that whole number will take like 3 pages. All right, just wanted to share that with you, and that's what scientific notation is. And if you guys haven't worked with it in a chemistry class or in high school and stuff, or in other algebra classes you've had, then you can just go to YouTube and type scientific notation, and I'll talk more about it if you, I don't know, if you want to look more deep into it. There's not much to it. It's basically some way of writing very, very large numbers in a very compact manner. That's all. All right, or small numbers for that matter. So let's move on to number 16. 4 FBI agents to be selected from a group of 9. In how many different combinations could this happen? Well, this one gives it to you, how many combinations. So you're trying to choose how many groups of size 4 can you create from the original 9 member in a group. And the command for that will just be combin 9, 4. And that'll just be 126. And that's the answer for that. The next one, again, the group is highlighted. So without even reading the problem, I kind of get a feel that this is a combination problem, because that's when the word group comes out. So you want to figure out how many ways you can create a groups of size 5 from 10 things. So combination of, again, 10 choose 5. You don't even have to think. It's straight up. You're just remembering when to use this shortcut formula. And again, the same thing for the next one. You see the group, and you have 12 faculty members, and you want to know how many ways you could put them in groups of size 5. So this will again be the combination of 12 choose 5, and that'll be 252, right? Sorry, I'm looking at the wrong one. That'll be 792. Okay. So that'll be a combination of 12, choose 5. Same as the next one. How many groups of size 5 can I create from 15 eligible employees? That'll just be a combination of 15 people being chosen 5 at a time. And that's 3,003 different ways you can do it. And the command is combin 15, 5. And that gives you 3,003. Just for the sake of doing the mathematics, if you were doing 15, 5 mathematically using the n factorial over k factorial n minus k factorial formula, this would have been 15 factorial divided by 5 factorial times 15 minus 5, which is 10 factorial. And then you'd have to simplify this. You'd have to write this as 15 times 14 times 13 times 12 times 11 times 10 factorial. And then you'd have divided it by 5 times 4 times 3 times 2 times 1 times 10 factorial. And then the 10 factorials would have canceled out, right? And then 5 and 3 is 15 would have canceled out with the 15. 4 would have canceled out with the 12. 2 would have canceled out with the 14. So the answer would have been 7 times 13 times 3 times 11, which I'm sure will give you 3,003 if you multiply it out. And that's how I used to do it as a math major, and that's how like you do it in algebra classes if you've had intermediate algebra. But in this course, you're the researcher, you're the social scientist, so you're not a student. So you kind of want to get the combination so you know what to do for your research project, and for you, that's what's important. All right, and that's the sort of a much better way of getting the answer than going through all that pain. So the answer for that is 3,003. Excellent. Let's move on to, so these were a whole bunch of questions on different MN rules and factorial rule and combination rules. Now let's sort of continue our journey through this module, getting closer to probability. And the next set of items you need to practice with is to create tree diagrams and construct sample spaces, because as you've noticed, to answer probability questions, you need to be able to construct a sample space so you can count the number of outcomes, so you could use that count in calculation of probabilities. So we're going to talk about tree diagrams and constructing sample spaces next in the set of exercises here. All right, let's look at number 20. Use a tree diagram to construct a sample space for tossing a coin 3 times and or 4 times. All right, well, let's look at these tree diagrams that I've constructed here already. So for a 3 coin toss, and we know it's heads and tails, you start with the first one. You toss it, you get heads or tails. And then from the head, so each one of these is called a node. So from this node, for the second toss, see, this is the second toss, you can still get a heads or tails. And if your first toss was tails, your second toss again could be heads or tails, and that's how you proceed. And your third toss again could be heads and tails, and that's where you stop. If I say 4 tosses, you go 1, you go 2, you go 3, and then you go 1 more out, so you go to the 4th toss. So you obviously will have more outcomes. Now, the MN rule could tell you the total number of outcomes for each one very simply, and you don't have to go through all this diagram construction. So if I say you have 3 coin tosses, you can use the MN rule. You have 3 positions, and each one could be heads and tails, so you have 2 choices for each position. So we all know, very simply, or could know, that there are 8 outcomes without even doing it, without even constructing it. But if someone says, I want you to tell me exactly what these outcomes are, then this 8 is not sufficient. And that's why you're going to need this tree diagram to be able to actually list every one of these outcomes. And why do you need to list these outcomes? Because, well, you'll eventually use these to calculate probabilities. Because if somebody asks you a question as to how many of these outcomes have exactly 2 tails in them, then you can just simply say, okay, I can count, since I have all the outcome, this one has 2 tails in it, this one has 2 of them, this one has 2 of them, and so there's only 3 outcomes that have exactly 2 tails in them. And this 3 is going to be very important in questions that have to do with probabilities. And the same way here. And the way you actually construct these outcomes is to actually follow these branches of these tree diagrams. So you follow the first branch, you get the head, 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 head. Follow the second branch, head, 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 tail. Head, head, tail, head. head, head, tail, tail, head, tail, head, 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 tail, head, tail, head, tail, tail, head, head, tail, 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 and so on and so forth. So that's how you construct these outcomes. So to construct them, you need a tree diagram. To know how many outcomes there are numerically, all you have to do is use the MN rule. Like for here, you have 4 coin tosses, so you have 4 positions, and each one could be heads or tails. So for each one, you have 2 choices. So 2 times 2 times 2 is 16. So you could guess, not guess, but you could use the MN rule to calculate how many outcomes there are. But if you need to actually list them, you have to use the tree diagram. Excellent. So let's move on, guys, to the next question. This is number 21. What is it asking us here? Some more tree diagram question. So you have, for breakfast, Robert always selects one of each item. Orange juice or grapefruit juice. So those are your first 2 choices. So again, when you're starting the tree diagram, you start from the center and then you go out based on your first 2 choices. Then from the tip of every one of these choices, you go out for the other 2 choices. So you basically just list the possible choices every time you branch out. So first you get an orange juice and grapefruit juice as a choice. Then if you get an orange juice, then you have a choice of getting eggs or hash browns. Same if you get a grapefruit juice, you also get a choice of getting eggs or hash browns. Now if you get an orange juice and you get eggs, then you have a choice of getting a toast and a bagel. So you just list all the possible choices after each one, and there's no more, so you stop there. And now if you want to know what the possible menu items are, you just follow these branches. So if I use the red color, the first one is orange juice, eggs, and toast. The second one will be orange juice, eggs, and bagel. The next one will be orange juice, hash browns, and toast. And so on and so forth. So that's how you construct the tree diagram for number 21. Alright, let's look at 22. It says 2 fair dice rolled. Find the probability of each of the following events. Hint, construct a sample space. It means list every possible outcome. Now we've done that many times before class started and during our conversations, and you should have this engraved and memorized in your memory, but I figured I'd put it here for you guys to see it one more time because this is homework after all. It's not an exam. During the exam, obviously the hint will not be given and this table will not be given. So you have to have this in your memory bank. Alright, so let's answer the question so we learn how to respond to these types of questions. It says, find the probability of getting an even dot on both dice. So even on the first one and even on the second one. Now, the total number of outcomes is 36, because there are 36 outcomes here. We know that. And what we want to know is, out of these 36 outcomes, how many of them have even dots on both dice? Well, this is not even. So none of these are, see, that's even, but this one is not even. So this row is out because all the first ones are not evens. This row out because this row, the first one's all 3s, so it doesn't matter what the second one is. This row is out too because the first ones are all 5s and 5s are not even. Now, this column is out because the second ones are all odds. This column is out, this column is out. So at this point, it's not that difficult for me to trace how many of these outcomes have both even numbers on both dice. This one's one of them, 2 and 2, they're both even. 2 and 4, 2 and 6, 4 and 2, 4 and 4, 4 and 6, 6 and 2, 6 and 4, and 6 and 6. So if I add the red circles, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 out of 36 outcomes that have even number on both dice. Now, of course, you're going to have to type this on a spreadsheet or a calculator of some sort, and you have to write the decimal value for probability. So 9 divided by 36. It's almost, it's 1/4, 25%. So, but we don't write it as 25%, we just write it as 0.25. All right, so that's how you do that one. Let's look at the next one here. It says getting a sum of 5 on both dice. Probability of getting a sum of 5. Again, my denominator is 36, and now I have to go back to this picture and figure out how many of these add to 5. That 1, 2, 3, 4. So there are 4 outcomes that add to 5. Correct? Perfecto. So that's 0.111 if I round it to 3 decimal places. And that's what you have to do. And the last one says getting an even number of dots on the first die and an odd number on the second one. So now here you have 2 of them, the one even on the first one and odd on the second one. Again, the total outcome is 36. And now I have to go back to this table again, and now you see why having this table in your memory is important. And if you can't do it in your head, and I can't, I usually always have to write it all out. So write it all out takes about 2 minutes, and then you can easily count what they're asking you to count. So here you're looking for the outcomes that the first one is even, second one is odd. Well, let's see. Even and odd, even and odd, even and odd, even odd, even odd, even odd. Even, odd. Let's see, what else? Even, odd, 4 and 5. Even here, even, odd. And these are all even here. There's no odd there. That's an even, odd. And there we go. So let's see. Here's an even, odd. And that's about it, I think. There you go. So those are the outcomes that are even first, odd second. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9 of those. So again, this is a quarter, 0.25. And that's how you answer number 22. All right, so let's move on to the next problem. Now you see why and where we use these sample spaces, and why is it that construction of these outcomes using tree diagrams is important. Because for questions like this, if a coin is tossed 4 times, what's the probability of getting 2 or more heads? So you're finding the probability of getting 2 or more heads when you toss a coin. Well, it's equal to, and you know probability is always out of the total, and the total number of outcomes here is 16. So you know the denominator is going to be 16. All I have to know is how many of these outcomes have 2 or more heads in them. So let's count. 2 heads, 2, 2 or more, that means 3 also. 2, 2, 3, 2, 3, 3, and 4 is more than 2. So that's it. See how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's why the answer is 11. And if you divide 11 by 16, you get 0.688 to 3 decimal places. And there's the answer for number 23. 24 says, on a multiple choice test, there are 5 possible answers. So the total number of possibilities is 5. If you make a random guess, that means one guess of those 5 questions, what's the probability that you're correct? Well, you're doing, this is pretty a simple exercise. Think about it conceptually. You're just making 1 out of 5 guesses, 1 out of 5 problems, 1 out of 5 choices. So the chances that you guess that right is 1 out of 5. Part divide by total. Now 1/5, and you divide 1 by 5, you just get 0.2. And that's the answer for that. Let's look at number 25. There are 7 cans of cola and 9 cans of Sprite. So cola is 7, Sprite is 9. If a can of soda is randomly selected, find the probability that is a can of soda, so probability of getting a cola. If you write it, so conceptually, it's the number of colas divided by the total number of total number of cans. Now, how many colas do we have? 7. Total, how many cans do we have? 16. So the answer is 7/16. And you use 3 decimal places, and the answer will be 0.438. Let's look at the last 2 here on this page, 26 and 27. We're tossing a coin 15 times, and they're asking us to find the probability of getting tails. The total number of tosses is 15. That goes to the denominator. And all I have to do is count the number of tails. 1, 2, 3, 4, 5, 6, 7, 8. So the numerator is 8. So the answer is 0.533, up to 3 decimal places. Excellent. And the same one for the other one. A die is rolled 20 times. The outcomes are given here. Find the probability of getting a 3. So probability of getting a 3 is a total number of rolls, which is 20. That goes to the bottom. And we're looking for the number of 3s. Probability of getting a 3. So that means you have to find a number of 3s. We get 1, 2, 3, 4. 1, 2, 3, 4, and I don't think there's any more 3s, so it's 4 out of 20. So the answer is 0.2. Okay, let's start with problem 28. If a card is drawn at random from a well-shuffled deck of cards, 52 cards, let's see if we can calculate the following probabilities. And once again, the probability of an event or an outcome is the number of times that event takes place. So the number of outcomes in that event divided by the total number of outcomes. So don't ever forget that. That's a fundamental probability question formula. So find the probability of getting a 7 is basically number of 7s in a deck of cards divided by the total number of cards. Well, how many 7s are there? 1, 2, 3, 4. And I'll erase this one. So there are 4 7s divided by 52 cards. So the answer is 4 over 52. But in this course for module 3, for probability, we are going to use 3 decimal places. So if I do 4 divided by 52 and round it to 3 decimal places, I get 0.077. And that will be the answer you will put on your test, or you'll select as a multiple choice response. What's the probability of getting a king? Same thing, number of kings divided by the total number of cards, which is 4 out of 52 again, because there are 4 kings and 52 cards. And it's 0.077. Find the probability of getting a black ace. Again, number of black aces divided by the total number of cards. The denominator is 52. Number of black aces is 2 of them. So the answer is 2 out of 52. And if I round it to 3 decimal places, I get 0.038. And that will be my answer. Find the probability of getting a red queen. The number of red queens divided by the total number of cards again. How many red queens are there? 1, 2. So it's 2 out of 52 again, 0.038. Let's look at find the probability of getting a spade, a red spade. Probability of a red spade. Number of red spades divided by the total number of cards. Let's look at to see how many red spades are there. The spades are all black. None of them are red. So there's 0 red spades in a deck of cards. So the probability is 0. Find the probability of getting clubs. Again, number of clubs divided by the total number of cards. How many clubs are there? There's 13 of each suit. So there are 13 clubs. So the probability is 13 out of 52, which is a quarter, 0.25. Find the probability of getting a face card. Again, number of face cards. Divide by total number of cards. Total number of cards is 52. Number of face cards is, there's 12 face cards. So it's 12 out of 52, which is 0.231. If you round it to 3 decimal places. And final probability of getting a 7 of hearts. The number of 7 of hearts divide by the total number of cards. The total number of cards is 52. And let's go back to the deck of cards and let's see how many 7 of hearts I have. There's only one 7 of hearts out of 52 cards. So the probability will be 1 out of 52, which is 0.019. Great. Let's move on to number 29, which seemed to be an addition rule. If a card is randomly drawn, find the probability of getting a black card or a face card, and this or indicates that you're dealing with the addition rule. And to remind you, probability of A or B for the addition rule was probability of A plus probability of B minus the probability of A overlap B, or AND, or intersection. All three of them will give you the same meaning. All right, so let's use that formula to figure this one out. Find the probability of getting a black card or a face card. Now, by using the definition of the probability addition rule, and given that this is an addition rule, first I define this as probability of getting a black card plus probability of getting a face card minus the probability of getting a black card overlap face card. In other words, how many face cards or black cards equals, well, probability of a black card, how many cards are black? Well, if I go back to the deck of cards, you find out that half of the deck is black, so it's 26 out of 52. So probability of a black card is 26 out of 52. Plus the probability of getting a face card, that's 12 out of 52. Minus the probability of getting a black card, that's a face card, or a face card, that's a black card. If you go back to the deck of cards, you realize that half of the face cards are black. So 1, 2, 3, 4, 5, 6. So there are 6 cards, face cards, that are black. So that becomes 6. And if you type this on Excel, straight up the way you see it, and I'll just write it up here for you guys so you see how you type this on Excel. It's a simple addition. Equals to, you type equal to, basically just type what you see, 26/52 plus 12/52 minus 6/52, and press enter. And that will give you the answer. And the answer is 0.615. So about 62%. Excellent. All right, let's move on to another addition rule problem. In a company, the probability an employee picked at random as an engineer is 0.63. So probability that an employee is an engineer is 0.63. Probability that the employee is male is 0.73. So here they've given you the probability. You don't need to divide anything. And the probability that employee is a male engineer, so the probability of a male overlap engineer is 0.54. And they want you to find the probability of getting a male or an engineer. And again, because of this or, it means I'm dealing with an addition rule, so I define it. Probability of a male or engineer is equal to probability of a male plus probability of an engineer minus the probability of a male overlap engineer. Now here, you simply have all the information you need. Probability of getting a male is given. You don't even need to look for it. It's 0.73. Probability of an engineer is given as well. You don't need to look for it or create it. It's right there. They've given it to you. And minus the probability of a male engineer. They've given you that as well. So you just need to add 0.73 to 0.63 and subtract 0.54 from it. And this gives you 0.82. And that's the answer. All right, let's look at another addition rule problem. A production line has manufactured 1,500 SSDs and 980 HDDs. These are different hard drives, solid state drive and high density drives. 10 of the solid state drives and 4 of the high density drives are known to be defective. If a quality control manager picks a drive at random for testing, what is the probability that so and so? All right, well, because of the OR, again, we notice this is an addition rule. So I will first define these questions. The probability of getting an SSD or defective disk will be probability of getting an SSD plus probability of getting a defective disk minus the probability of getting a defective overlap SSD. Well, what's the probability of getting an SSD? The probability of getting an SSD is the total SSDs, which is 1500, divide by the grand total, plus probability of getting a defective is the total number of defectives, which is 14, again divide by the grand total. And the drives that are the SSDs that are defective, SSD defective is 10, the overlap, so that's 10 out of 2480. And those are the defective SSDs. Now, how do I do this? I simply go to a spreadsheet and I do exactly what I had asked you guys to do earlier. So you type equal to 1500 divide by 2480. And I'm doing this on a spreadsheet in front of me as I'm speaking it to you, plus 14 divide by 2480 minus 10 divide by 2480. And if you type that on Excel, you get 0.606. Very good. Now the next one says probability of HDD or not defective. So that'll be probability of HDD plus probability of not defective minus the probability of HDDs that are not defective, or the overlap of the two. All right, and here probability of high density drive is the total number of high density drives, which is 980, and that'll be divided by the total or the grand total, which is 2480, and then plus the probability of being not defective, and the total number of non-defectives is 2466, and divide again by the total number of drives, which is 2480, and then minus the number of HDDs that are not defective, and it's their overlap, if you recall, and the number of HDDs that are not defective is 976 of them. And that probability becomes 0.996 if you round it up to 3 decimal places. Probability of getting an SSD or an HDD will be probability of getting an SSD plus probability of getting a high density drive minus the probability of getting their overlap, SSD overlap, HDD. And this overlap is also used as a union symbol, intersection symbol, and the OR is the union symbol. Anyhow, so if I do this probability of SSD, there's 1500 SSDs, divide by the total number, plus there are 980 HDDs, and there is no SSD that an HDD, they're just two different products, so here the overlap is 0, so the answer is just 100%. Obviously, if that's all you got, probability of, if you pick a disk at random, will be either that or that is 100%. All right, excellent. So let's move on to the next additional problem. Here I have a blood type table here for patients, and they're asking me to find a probability that if you randomly select someone, they will have a B group or have a positive blood type. So we're trying to find a probability that somebody belongs to an AB group or have a positive blood type. Now again, if I expand the addition rule, probability of getting an AB person plus probability of having a positive blood type minus the probability of AB intersection positive, which is the overlap. Probability of getting an AB blood type is 37 out of 305. Probability of getting a positive blood type is 166 out of 305. Minus the probability of the overlap of AB and plus. This is AB and this is plus here, so that's the overlap. So it'll be minus 30 divided by 305. And that becomes 0.567. And that's the answer for number 32. Excellent. Let's move on to a few of the mixed problems here. Just reviews everything we've done before. An ice cream store offers 3 types of cones and 31 types of flavors. How many different single scoop ice cream cones is it possible to buy at the store? Okay, this is a straightforward MN rule, which you have to multiply the number of choices. Here you have 2 positions per se. You have types and flavors. So you have types and flavors. And you have to multiply them. Now, what are the number of choices I have? The number of choices for types is 3. The number of choices for flavors is 31. So if I just simply multiply them, I get 93 different outcomes. So it's basically product of choices again. The MN rule, just to remind you, which is always a product of choices. The number of choices. Very good. The next one says 34. How many different 4-letter words, including nonsense words that don't have to make sense, it's just a mathematical rearrangement, can be made from the letters of the following word? So I have 1, 2, 3, 4, 5, 6, 7, 8. So the total number of letters here is 8. Just write that so I won't forget. Now it says 4-letter words, so I have to have 4 positions. So here are my 4 positions, and it says if the letters cannot be repeated. So I start with 8 choices for the first position, but if I put one of the letters in there, then I have 7 letters to choose from for the second position, and 6 letters to choose from for the third position, and 5 letters to choose from for the last position. And if the MN rule tells me that if I multiply them, I'll get the answer, which is 1,680 different words could be created. For the second one, it says if the letters can be repeated. So I have again 4 positions, and this time the letters could be repeated, so I have 8 choices for the first one, but since I can use the same letter for the second position, I have 8 choices there and the same for everything else. And that's 4,096 outcomes. Let's move on to number 35. To buy a computer system, a customer could choose one of 4 monitors, one of 2 keyboards, one of 4 computers, and one of 3 printers. What are the total number of different systems they could put together? Well, again, first and foremost, let's look for number of positions. And number of positions are monitors, keyboards. I have monitors at 1 position, 2 positions, 3 positions, 4 positions. So I'm just going to write them here. First, second, third, and fourth. These are monitors. These are keyboards. These are computers, and these are printers. You have 4 monitors. Those are the number of choices. 2 keyboards, 4 computers, and 3 printers. So the MN rule says multiply. So the answer is 96 possible systems you can put together. Excellent. Let's look at this one, number 36. You have a 9-digit phone number you're working with. So I'm just going to draw 9 digits here, or 9 positions. Excellent. So now, here we have some requirements that they've given us. It says the first two digits are the area code, which is 03, and they're the same within a given area code. So the first two has to be, so the first digit has to be a 0. So it has to be a 0. Well, that means I only have one choice for that position. The second digit, the problem says, has to be a 3. If the second digit has to be a 3, then again I have no choice. There's only one way I can get a 3 out of 10 numbers. And I have 10 digits, mind you, in this world. 0 to 9. Alright, now for the third digit it says the last 7 digits are local numbers and cannot begin with a 0. So the only restriction on the third position is that it could be any of those 10 digits except 0. So anything except 0, which means I have 9 choices for that one. And then the rest of them could be any digit and they could repeat, so I have 10 choices for the rest of them. So if you think of it like that, it's not that bad. So the answer is basically 9 with 6 zeros in front of it. And that's your answer. Let's look at number 37. A student can select one of 6 different math books, one of 3 different chemistry books, and one of 4 different English books. How many ways can a student select one of each class? So obviously, this is an MN rule, and you have 3 positions. You have the math books, you have the chemistry books, and you have the English books. Math, chemistry, and English. And then the number of choices, you get 6, 3, and 4. And if I multiply the number of choices, which is what MN rule asks us to do, I get 72. Let's move on here. A man has 3 different suits for number 38, 4 different ties, 5 different flip-flops. How many different pairs? I mean, how many different ways could this man wear a suit, shirt, and a pair of shoes? So again, it's simple MN rule. I got 3 positions: suits, ties, and shoes, flip-flops. I'm assuming they're the same at this point in terms of vocabulary. So again, you have suits, ties, and flip-flops, and the choices are 3 suits, 4 ties, and 5 different flip-flops. And if I multiply them, the MN rule tells me there are 60 outcomes. Moving on, in a certain country, license plate numbers have 3 letters followed by 4 digits. How many different license plate numbers can be formed? Well, you have 3 letters and 4 digits. So I have letters and digits. You have 3 letters, so you have 3 choices for those, and 4 digits. Okay, and for number 39, we have a 7-digit license plate where it says the first 3 digits, the first 3 characters could be letters, and the last 4 characters have to be digits. And they want us to find how many different license plates there are. And the instruction says the letters and the digits may be repeated. Very good. So if I have 3, the first 3 have to be letters, and I have 26 letters in the alphabet. So I'll use 26 here for the first position. And it says letters and digits may be repeated, so you could use the same thing, same number of choices for the second position and the third position. And then since we have 10 digits all in all, and you have 4 of those, and they could be repeated, so you just get 10, 10, 10, and 10. So, and again, that's just basically the MN rule. So it's 26 times 26 times 26, and then you just have to put 4 zeros in front of it. So 17,576 with 4 zeros in front of it. That gives us 175 million possible different license plate numbers. Excellent. Moving on, suppose an organization elects its officers from a board of trustees. If there are 30 trustees, in how many ways could the board elect 4-member groups for the finance committee? And again, we want to know how many groups of size 4 can we create from 30 people. And that's always a problem of combination. As soon as they're asking you to figure out the possible number of groups you can make at a certain size from a certain group of people, that's definitely a combination scenario. And basically you're writing combination of 30 people chosen 4 at a time, as that's how you read it. And if you use the combin parentheses 30 comma 4, you will get your answer of 27,405. So that will be your answer. In how many ways, for number 41, can a group of 3 members be chosen from a club with 9 members? Again, basically you're trying to figure out how many 3-member groups can you make out of 9 members. And again, that's just a question of combination of 9 choose 3, which I'll give you 84, which is combin 9 choose 3. Okay, moving on to look at a review of a tree diagram, 2 freeways from Smallville to Narnia. So if that's Smallville and this is Narnia, there are 2 freeways that get there, Freeway 1 and Freeway 2. Those are your 2 branch options. And then from Narnia to Rivendell, they got 4 highways, and that's Rivendell there. So there you have 4 ways to get from Narnia to Rivendell from either freeway. And that's how we set up the tree diagram. So the total number of routes, we could have figured out easily using the MN rule by multiplying 2 to 4. So we know there are 8 outcomes. But actually listing them, you just have to follow the branches. Freeway 1, Highway 1, Freeway 1, Highway 2, Freeway 1, Highway 3, Freeway 1, Highway 4, and then Freeway 2, Highway 1, and same combinations, Freeway 2, Highway 2, Freeway 2, Highway 3, and Freeway 2, Highway 4. And these are your 8 outcomes. And recall, this is called the sample space. Collection of all the outcomes. Very good. Let's continue our review of probability questions here, or probability chapter questions. They're not all probability questions. Some of them are counting questions. Just like number 43. What is the total number of outcomes when a coin is tossed 12 times? Well, if you were to do this with the MN rule, you'd have to draw 12 positions and give 2 choices for each one, because it could be heads or tails. But you guys remember the formula 2 to the n you can use every time they're asking you to find the total number of outcomes for experiments that have 2 possible outcomes for each trial. And for that, you could always use the 2 to the n formula. So if there are 12 coin tosses, that'll just be 2 to the power of 12. Or basically, if you look at it from the MN point of view, it's just 2 multiplied by itself 12 times. So you have basically 12 positions and 2 choices. So the answer will be 4,096. Look at number 44. You have a 5-character code. 1, 2, 3, 4, 5. And same for the other one. 1, 2, 3, 4, 5. And we're using letters of the alphabet for each character. So it's 26 choices. How many different codes could be created? If, for the first one, it says may be repeated within a code, so characters could repeat. So you have 26 choices for the first one. Same for the second, third, fourth, and fifth. Because it can be repeated. So this is basically 1, 2, 3, 4, 5. This is 26 to the 5th power. And if you do that on your calculator, 26 to the power of 5, or on Excel, you get a big number. So let's see, get 1,188,1,376. So 11 million of some sort. And if they cannot be repeated, so you get 26 choices, but then you can't use one of them that you choose for the first characters. You get 25 choices for the second one, 24, 23, and 22. And that's what you got to multiply together. So if you use a spreadsheet or a calculator, 26 times 25 times 24 times 23 times 22, and that will give you 7893600. So 7.8 million. Great. Let's go to number 45. Professor Bedalian has 8 test problems on combinations and 5 on arrangements. How many ways can he select one of each? Again, basic MN rule, 2 positions, combinations, and arrangements. 8 choices for the first position, 5 choices for the second position. So the answer is 40 different choices. Moving on. The following table lists the great distribution of a randomly selected stats class from a university. Use the data in the table to find the probability of getting an A in the class based on the data provided. So probability of getting an A, if you recall, by the definition of probability being the ratio of the number of outcomes, is the number of A's divided by total number of letter grades. Well, what's number of A's? There are 8 A's divided by the total number of grades, which basically will be 8 plus 6 plus 15 plus 2 plus 5. So if so you add the denominators, the numbers in the denominator, and that gives you 36. That's right, it's 7 plus 15, 22 plus 8, 30 plus 6, 36, and that gives you 36 in the denominator, and you have 8 in the numerator, so 8 divided by 36 is 0.2222. Let's look at number 47, 12 Republicans and 35 senators. If a senator is randomly selected, what's the probability a senator will be a Democrat? Well, probability of a Democrat will be the number of Democrats divided by the total number of senators. Well, how many Democrats are there? Well, if there are 12 Republicans and 35 senators, that means the rest of them are Democrats, right? So if 12 Republicans and 35, so basically 35 minus 12, that'll give you the number of Democrats. So the number of Democrats will be 23 divided by the total number of senators, which is 35. So you use Excel or your calculator or your cell phone, and 23 divided by 35 is 0.657. Basic classical probability where you part divide by the whole. Excellent. Let's move on to 48. Professor Bedadian has selected 12 questions for a probability test from his test bank of 300 questions. How many different versions of the test can he create? A lot of different versions, but since you want to figure out how many versions of size 12 from 300, that's a C312 issue. It's a combination problem. And if you do that on Excel by doing combin 300, 12, you get the following answer, which may not make sense to you guys if you haven't seen scientific notation displayed in Excel. That basically is scientific notation, and it means 8.87 times 10 to the power of 20. And we talked about this. This is just a way of writing very large or very small numbers. Basically what that means is if you write 8, 8, 7, and you could basically write the rest of the digits too. And all you have to do is take the decimal value there and move it 20 units to the right. So from here, I have to move it 20 units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And you fill in with zeros, and that's the number they're talking about. And now you see that's why imagine you would want to write this number a whole bunch of times every day if that was your job. So that's why they created this scientific notation. It's quite interesting, and if you guys haven't seen it, you could just search it on a search engine and read more about it, or go to YouTube and look at some scientific notation for very small or very large numbers. Anyhow, so that's the answer for that. Too many ways, too many options he has. Moving on to number 49, a sample space consists of 24 separate events, equally likely. What is the probability of each? Well, 1 out of 24. So that's an easy one. Oh, come on. There we go. Moving on for number 50, and here's some multiple choice questions. Given the 35 days in May and 365 days in a year, if a person is randomly selected, find a probability his or birthday is in May. So that's just giving the piece divided by the whole. So it's 31 divided by 365. A bag consists of 2 red marbles, 3 blue marbles, and 5 yellow marbles. If a marble is randomly selected, what is the probability that it is blue? Well, the probability of blue is the blue marbles, which is 3, divided by the total number of marbles, which is 5 plus 3, 8 plus 2, 10. So the answer is 3 out of 10. Very good. Moving on. Which one of the following cannot be a probability? That I'm sure you guys could pick up pretty fast. You can never have a minus number for probability, or a number greater than 1 for that matter. For 53, a card is drawn from a well-shuffled deck of cards. Find the probability of drawing a face card or a 4. Well, if you do this here, probability of drawing a face card or a 4 is probability of getting a face card plus probability of getting a 4 minus the probability of getting the overlap of a face card and 4, which we all know doesn't exist. So basically we have probability of a face card, which is 12 face cards out of 52 cards, plus probability of getting a 4, which is 4 out of 52. And that's 16 out of 52. And that's none of these, so I guess we could reduce this. They want us to reduce it. So divide both of them and reduce them by factor of 4. I get 4/13. And there you are. So that will be my answer. And same as number 54, we have if one of 87 flights is randomly selected, that's parts A and B. So they're giving you this table. They call them contingency tables. So if one of 87 flights is randomly selected, find a probability a selected flight arrived on time. Well, this is a single probability. So what's the on-time flights? There's 76 flights that are on time. Divide by the total number of flights, which is 87. So that would be my answer for that. And for part B, that's an addition rule. It says find a probability of getting a flight that's on time or upstate airline. Okay, and if I break that down, minus the probability of on time, overlap, upstate airline. So you get probability of being on time. You get 76 flights that are on time, divide by 87 total. Plus the probability to get upstate airlines, you get 48 of those. Divide by the total. And the overlap, it's 43. Divide by 87. And that is 0.931.